Hello everybody. Today I am going to discuss some important numerical problems based on differentiation from the chapter work, energy and power. So in first question, a body initially at rest, it undergoes one dimensional motion with constant acceleration. The power delivered to it at time t is proportional to t to the power half t to the power 3 by 2 t square. Here u is 0, which is initial velocity. Now using v equal to u plus at, we get v equal to at, and power is written as F into v. F is replaced by ma, v is replaced by at. So finally we are getting p equal to ma square t. Here you can see m and a are constant, so p is directly proportional to time. So the correct answer is option 2, that is t. Power is directly proportional to time. Now question 2. A body is moving unidirectionally under the influence of a source of constant power. Its displacement in time t is proportional to t to the power half t to the power 3 by 2 t square. देखो बच्चे, पावर कांस्टेंट है तो इसलिए p इक्वल टू के एक कांस्टेंट है. पावर को लिखेंगे एफ बी. एफ इज रिप्लेस्ड बाय एम ए, सो पावर इज नाउ एम ए इंटू वी and a is written as dv by dt. So from here we can write, from this equation we can write v dv equal to k dt by m. Okay, अब इसको इंटीग्रेट करेंगे. इंटीग्रेट करने के बाद यहाँ हमें मिल रहा है v इक्वल टू रूट अंडर 2 के टी बाई एम. और इस वेलोसिटी को dx बाई dt लिखने के बाद dx एक साइड रखेंगे और बाकी टर्म्स को दूसरे साइड ले जाएंगे और ये इक्वेशन 1 को इंटीग्रेट करेंगे. तो इंटीग्रेट करने के बाद हमें मिल रहा है x इक्वल टू 2/3 रूट अंडर 2k बाई एम टी टू द पावर 3/2. तो इस इक्वेशन को हम लिखेंगे, यहाँ पे 2/3 रूट अंडर 2k बाई एम कॉन्स्टेंट है, इसलिए x varies as t to the power 3/2. So here your correct answer is option 3. Now question 3. A body of mass m accelerates uniformly from rest to velocity v1 in time t1. Find the expression for the instantaneous power delivered to the body as a function of time. So here let us suppose that a be the uniform acceleration of the body. Then we can write v1 equal to 0 plus 8 t1 because the initial velocity is 0. So a is v1 by t1. Now velocity of the body at instant t is written as v equal to 0 plus at equal to v1 by t1 into t. Now instantaneous power p equal to fb. F is replaced by ma, so it is mav. Now putting a equal to v1 by t1 and v equal to v1 by t1 into t, we get power equal to mv1 square t by t1 square. Now question 4. A locomotive of mass m starts moving so that its velocity varies according to the law v equal to alpha root s, where alpha is a constant and s is the distance covered. Find the total work done by all the forces acting on the locomotive during the first t seconds after the beginning of the motion. To find the work done, we will have to find the force and distance covered. Okay, so here the given condition is that v equal to alpha root s, which is written in this way. Okay, and acceleration. To find the acceleration, we differentiate velocity and now acceleration is half alpha s to the power minus half into v, and finally after replacing v we get a equal to half alpha square. Now we can find the value of force, which is half m alpha square. To find the distance covered by the locomotive in first t seconds, we can write s equal to ut plus half at square. Here initial velocity is 0, so s equal to 1 by 4 alpha square t square, and work done w equal to fs. You can put the value of f and s, and you will get w equal to 1 by 8 m alpha to the power 4 t square. Now question 5. A body constrained to move along z-axis of a coordinate system is subject to a constant force F equal to minus I plus 2j plus 3k Newton, where I, j and k are the unit vectors along x, y and z axis of the system respectively. What is the work done by the force in moving the body at a distance of 4 meter along the z-axis? So here the displacement along z-axis can be written as s equal to 4k, okay, where k is the unit vector along z-axis. So this is the displacement and this is the force, and work done w equal to f dot s. So after taking the dot product we get work done equal to 12 joule. Now question 6. A body of mass 5 kg is moved along a straight line and its displacement x varies with time t according to the relation t equal to root x plus 1. Find the work done in moving the body for 10 seconds. Okay. Here given t equal to root x plus 1, which is further written as x equal to t minus 1 whole square, which is t square plus 1 minus 2t. Now v is replaced by dx by dt. So to find the velocity, we differentiate equation 1 with respect to t. Then we get v equal to dx by dt equal to 2t minus 2. And when we differentiate the velocity, we get acceleration, which is 2 meter per second square. Now F equal to ma, which is 5 into 2 equal to 10 Newton. Okay, now initial displacement at t equal to 0, you can easily find it, x naught equal to 1 meter, and displacement at t equal to 10 second, you can easily find by putting the value of t equal to 10 in this equation. Okay, you can get x10 means displacement in 10 seconds. Okay, so which is 81. Net displacement x10 minus x naught equal to 80, and work done w equal to fs equal to 10 into 80, which is 800 joule. Now question 7. A particle of mass m moving in a straight line with retardation proportional to its displacement. Find the expression for loss of kinetic energy for any displacement x. So here given retardation directly proportional to displacement. So we can write retardation means negative acceleration. So minus a equal to kx. Okay. Now a equal to dv by dt. So dv by dt equal to minus kx, equation 1, and dv by dt is further written as dv by dx into dx by dt, and dx by dt is replaced by v. So we are getting v dv by dx equal to minus kx. Now v dv equal to minus kx, integrating v dv equal to minus kx dx. Okay. So we get, here you can see what we are getting after integration. After integration we are getting v square by 2 and the limit is u to v. Okay. So it is now half v square minus u square equal to minus half kx square. Multiplying this equation by m on both the sides, we are getting the loss in energy, that is half mu square minus half mv square equal to half mkx square. This is the loss in energy. Okay, loss of kinetic energy. So question 8, the block of mass m moving on frictionless horizontal surface collide with the spring of spring constant k and compresses it by length L. Find the maximum momentum of the block after collision. Okay, so here you can see this is the block and this is spring. Let us suppose that the velocity of the block be v. When the spring is compressed by length L, potential energy is stored in the spring, which is given as half KL square. And the kinetic energy of the block is half mv square. Okay, so we can write half mv square equal to half KL square, and we know that momentum is mv, so here we can multiply and divide this by m. Okay, so we are getting p square equal to m KL square, where p is momentum and p equal to mv. So p equal to, now p equal to L root mk. So this is the maximum momentum of block after collision. Okay, so here you can see p equal to L root mk if no energy lost during collision. Question 9, an object of mass 3 kg at rest. Now if force F equal to 6t square I plus 4t j Newton applied on the object, then find the velocity in meter per second of the object at t equal to 3 seconds. Since F is given and F is written as ma, A is written as dv by dt, so dv equal to F by m dt. Okay, now integrating on both the sides, we are getting velocity equal to 1 by 3 into 2 tqi plus 2t square j. Velocity at 3 seconds is given by, to find the velocity at t equal to 3 seconds, we put t equal to 3 in this equation. Okay, so we can get b equal to 18i plus 9j meter per second. This is the answer. Okay, velocity of the object at 3 seconds is given by 18i plus 9j meter per second. Now question 10, so that coefficient of restitution for one dimensional elastic collision is equal to 1. We know that when the collision is elastic, then linear momentum is conserved and kinetic energy is also conserved. So consider the conservation of linear momentum. We can write m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. Okay, so after rearranging, we can write m1 into u1 minus v1 equal to m2 into v2 minus u2. This is your equation 1. And kinetic energy also conserved, so we can write total kinetic energy before collision equal to total kinetic energy after collision. So now after rearranging, we get equation 2. Okay, so from equation 2 and 1, we get v2 minus v1 equal to u1 minus u2, and according to the definition of coefficient of restitution, when we write E equal to v2 minus v1 by u1 minus u2, this is equal to 1. So this proves that coefficient of restitution for one dimensional elastic collision is equal to 1. Thank you for watching this video. Do not forget to like, share and subscribe. Thank you very much.